All right, it is 10, so we will get started for today. Let me get the PowerPoint up. And before I do that, I have to open up a second PowerPoint that I forgot, so I'm going to do that really quick. Right. All right, so what we were talking about last week is that we were talking about kinetic molecular theory. That is a theory in which we can begin to understand gases. And basically, the three main principles of gases, and one sec. Yeah, sorry, I'm gonna get out of this for 1 second because it is not sharing correctly on my screen. There we go. So the three principles are kinetic energy and temperature are proportional. Oops, that's a bad proportionality sign. And that's where we ended off on Friday, was solving for kinetic energy and molecular velocity. Our other principles of this theory is that gases have no volume. They don't really take up space. Again, that's an assumption that's relatively true. Gas take up very little space, so we can say they basically take up no space, and the collisions are elastic. That is, gas molecules bounce off each other like billiard balls. Right. And like I said, on Friday, we were talking about kinetic energy and molecular velocity. All right, so what we're going to begin with is just a question to think about molecular velocities and temperature. So I have two different molecules, A and B. They're the same temperature. Which molecule has the higher molar mass then? I have a poll for this. So what I want you to do is don't answer in chat. Don't answer in chat. Look at that. Look at that graph and just say, okay, if these molecules are the same mass and my velocity is on the y-axis, or sorry, my velocity is on the x-axis, and my percentage is on the y, which has the higher temperature. So velocity is on the x, percentage is on the y. Let me get that poll going now that we had a little bit time to see it. So which molecule, or sorry, I did the question a little bit wrong. They're at the same temperature. Which molecule has a higher molar mass? So same temperature, which one has the higher molar mass? It's a Monday. I guess I don't know how to read quite yet. Same temperature, different masses. Based on their speeds, which one's heavier? Right. So let's take a look at this poll. And yeah, so the majority of you are right. A is heavier, right? So remember, when we're talking about velocity, that is speed. Well, it's not quite speed, but it's like speed. Velocity is dependent on two things. It's dependent on mass and temperature for gas, right? So basically, when we're thinking about velocities, the more massive a gas molecule is, the slower it will be. And that all relates to kinetic energy. If we go back, so let me stop sharing this. If we go back to our molecular velocity equation right here, our molecular velocity, this U, in the denominator, we have molar mass. So the bigger the molar mass, the smaller the velocity. So that is why A has the bigger molar mass based on our graph. Any questions about looking at this graph, figuring out what it's telling us? Because reading graphs is like one of the most important, well, I don't know if it's the most important, but it's a very important skill to have. There's been many of times when I've been on the internet and somebody's making a wild claim and they show a graph and it's like, you don't even know how to read the graph because the graph is not backing up your point. But anyways, any questions about this question? Okay. If not, we will go on to our next slide here. Right. So here we have the same molecule. This is the question I was thinking of. The same molecule at different temperatures. What temperature is greater? Again, I'll put up a poll. So it's the same idea. We have molecular velocity on the X, percentages on the Y. Which one is a hotter temperature? Temperature 1, temperature 2. T1, T2, same molecule, different temperatures. Right, so most of us have voted, so let's take a look. So this was a little more even compared to our last question, but here T2 is correct. So we said velocity and mass are inversely proportional. The heavier you are, the slower you go. Well, velocity and temperature are directly proportional. The hotter you are, the faster you go. So here, T2, more molecules on average are going faster than in T1. On average, they're going slower. So that means T2 is the hotter temperature based on our velocity equation. Any questions about question 3 here? All right, let's move on then. So I'm going to skip mean free path diffusion in a fusion. I'll go over the terms. So we should know what diffusion means in a fusion, but I'm not going to go over Graham's law of a fusion. That basically just tells you the speed of a fusion. But let's just go through the terminology. The terminology is important to know. So When we measure distances in gas, what we really are measuring is what's called the mean free path. It's how far does a gas molecule travel before hitting something, right? And the more concentrated a gas is, the lower the mean free path. So higher concentration, lower mean free path. Because if you're very concentrated, there's other gas molecules around you, and you're going to hit those other gas molecules. While if you're in a vacuum, there's nothing around you, so your mean free path will be near infinite in a true vacuum because there's nothing to hit. Diffusion is the random spread of molecules from high concentration to low concentration. And I do want to emphasize, this is random. Like, molecules don't know, like, oh, I'm highly concentrated. I'm going to move to low concentration. Like, they don't have some thought process, right? This just happens based on random movement, right? So, like, I don't know, an example would be if I had 50 cats in a room, and then I just removed all the walls of the room, they would just randomly walk everywhere, and there would be less cats in that room. They would diffuse out, just random movements. While effusion, so effusion is if I have a container, and outside that container is the vacuum. If I poke a hole in that container, they'll go through that hole into the vacuum. It's similar to diffusion, in that we're going from high concentration to low concentration, but it's just a little more specific in our definition. And Graham's law of effusion is how we can measure the effusion of two different gases and either figure out an unknown molecular weight or figure out an unknown traveling speed, rate of effusion. But like I said, we're going to skip that problem. For time's sake, we're going to skip Graham's law of effusion. And I just want to remind you of kinetic molecular theory. I mentioned this at the very beginning. I'm not going to go through it again, but I do want to just talk about real gases, right? So kinetic molecular theory in the ideal gas law is what we use to describe gases. However, no gas behaves like an ideal gas, right? An ideal gas is made up. There's no such thing as an ideal gas in this world. So here is a critical thinking question for everybody. If ideal gases are made up, if they don't exist, why do we have the ideal gas law? Why do I go through the trouble of teaching you the ideal gas law and how ideal gases exist if they don't exist, or rather how ideal gases behave? Does anyone have a possible answer why we use the ideal gas law even though it's ideal gases are completely fake? Because there's no such thing as a particle that does not take up a volume. That's impossible. There's no such thing as a completely elastic collision. That's impossible. So why do I bother with the ideal gas law? What's the point? You want to have any ideas, any theories as to why we even teach the ideal gas law? It shows the interaction between gas molecules. To simplify it because it's similar to reality and makes it easier. That's what I would go with. The ideal gas law is close to reality, and it really does simplify all the math. Yes, it does tell us how gas molecules interact. And to capture a real gas, though, Like if I wanted to do a calculation on a real gas, you would have to have a lot more parameters and your equation gets way more complicated. But if we look at the next image, we will see that under normal conditions. So what I'm showing here on the x-axis, this is pressure in atmospheres. An ideal gas is in red, while a real gas is in green. And what you can see is that from roughly 175 atmospheres and below, so like from 1 to 175 atmospheres, there's no difference between an ideal gas and a real gas. They behave the exact same way based on our calculations. However, as you get to higher and higher and higher pressures, gases actually having a size matter now. And so what happens at higher pressures is that you do see a difference. So on the y-axis, we have volume. So pressure and volume between ideal gases and real gases start to differ at very high pressures. And so we have different terms to deal with that. However, if you are talking about a gas, like on Earth, not under crazy conditions, because we live at 1 atmosphere, the ideal gas law is perfectly fine for describing the behavior of those gases. Does that make sense? Any questions about that idea of why we have the ideal gas law versus real gas? All right. To correct for a real gas, we have to have these correction factors, and this is called the van der Waals equation. So we have to correct for 2 things. One, we have to correct for intermolecular forces. Okay, so let's break down that word, because if you continue through chemistry, you're going to see the word intermolecular a lot. All right. So I'm from the great state of Michigan, and I know how to draw Michigan way better than I know how to draw Texas, because Michigan's a giant hand, right? And there's highways, and below Michigan, I know for most people not from the Midwest is a giant question mark that you probably assume is full of cornfields. So below Michigan, we have 2 states. We have Indiana, and we have the armpit of America, which is known as Ohio, right? Now, highways that connect between different states. So if I have a highway, and this is basically what the highway system looks like in Michigan. And sorry, it always peeves me when you draw Michigan and you don't draw the Upper Peninsula. Again, if you're not from there, you probably don't realize Michigan has 2 peninsulas. Anyways, the highways that connect states are called interstate highways. So when you see the word intermolecular, what that is talking about is the forces between 2 different molecules. Just like an interstate is a highway that connects 2 different states. Intermolecular are forces between 2 different molecules. So in the ideal gas law, we assume molecules don't interact. They actually do. And so we have to affect that by having this A term. So this A term, this A NV squared term, corrects for our intermolecular forces. And we also have to correct for volume. We said that molecules don't have volumes, which isn't true. Gases do have volume. So we have another correction term for that. And what you can see here on this graph, this purple line is the ideal gas law. Here's a bunch of different gases at high pressures. And you can see we deviate from the ideal gas law a ton. If we're at 1 atmosphere though, we're pretty much the same. But but once we get away from 1 atmosphere, the ideal gas law starts to deviate quite a bit. So that's when we have to have these correction terms. Yes, Ohio is the armpit of America, though. Being from Michigan, I'm allowed to say that. All right. Now, what I want from you is I don't expect you to memorize. Well, I don't expect you to memorize any equation. But again, for time, I'm not going to go over examples of van der Waals equations because it's more important that we know PV equals nRT and how to use that. What I want you to know from this slide is what does the van der Waals equation correct for? And it corrects for intermolecular forces and it corrects for volume. That's what I want you to know. It corrects for intermolecular forces and it corrects for volume of a gas. Well, you got me good. I have no problem offending Ohioans by mocking their state, though. I guess it's like Texas and people from Oklahoma. You guys like mock each other all the time. The same thing between Michigan and Ohio. Any questions, though, about what I expect for the van der Waals equation? Okay, if not, I'm just going to update my highway system. It actually goes like that and like that. All right. So that's all for this PowerPoint. Let's move on to the PowerPoint we had for today. Again, I'm not going to go over question 5 where we use the van der Waals equation just for time's sake and simplicity's sake, really. 99.9% of people who go through Gen Chem 1 never use the van der Waals equation in anything. So we are going to skip that. And we're going to go to today's PowerPoint. All right. And now we are getting away from gases and we're going to talk all about energy. And our definitions are energy is the capacity to do work. So that is the scientific definition of energy. Can you do work? If so, you have energy. What is work? Work is simply force over a distance, right? So let me do some examples of that. If I have my cup and I just hold my cup, I'm doing 0 work. You can imagine this is like a dumbbell too. If I have a dumbbell and I'm holding a 20-pound dumbbell and just holding it up, my arm will get tired, but technically I'm not doing work. When I start to move my cup, I am now doing work because work is force over a distance. So I'm moving something, which is using force, and I'm moving it across the distance. So keep that in mind for work. You have to have some kind of distance in there for our definition of work. Right? And our other type of way we define energy. So really what I'm doing here is energy is made out of 2 things. It's made out of work and it's made out of heat. That's all it is. Heat is the flow of energy caused by a difference in temperature. So if 2 things are different temperatures, they are going to exchange energy until they are at the same temperature, right? And we have 2 ways to describe this change of heat. It's called exothermic or endothermic. And when we're describing this, we have to be aware of some terms. So whatever we're studying, let's say we have a glass of water, we call that the system. So whatever we're interested in, we call that the system. Everything that's not the system, we call the environment. or we'll also call that the surroundings. Usually called the surroundings. In this definition, I have the environment. So if heat leaves my system and goes to the surroundings, that's called exothermic. The way to remember exothermic is it has the word EX in it, like exit. Heat is exiting the system. It's exothermic. While if heat goes into, wow, yellow is a horrible color, isn't it? Let me go with green. If heat goes into my system, that's called endothermic. It's going into my system, or in, endothermic, exothermic. So those are some of our definitions there. Now we have different types of energy. So now this I usually do as a demonstration too. So let me go back to the camera. So different types of energy. One, we have potential energy. Potential energy is the energy of position, usually. So a pen, the higher I hold a pen, the more potential energy I'm giving it. Because when I let go of the pen, whoa, I dropped it. When I let go of the pen, gravity will take that pen and move it down faster and faster. The higher I hold the pen, the faster it will move. It will be moving until it hits the ground at terminal velocity if it gets there. So potential energy is the energy of position. And it's easiest to think about that when we think about gravity. The higher you are, the more potential energy you have. Kinetic energy is the energy of movement. So when I build up this potential energy and let go of the pen, all of that energy, all that potential energy converts to kinetic energy. So potential energy is the energy of position. Kinetic energy is the energy of movement. We have thermal energy, which is the energy of heat. Now, when we learned about the laws, our laws at the very beginning of the class, one of the laws we had was conservation of energy. Energy cannot be created or destroyed. It can only change shape, right? So when I'm working with this pen, if I move it higher, I'm giving it potential energy, right? When I let go of it, that is kinetic energy. When it hits my computer, what happens to all that energy? Where's the energy go? And that's a question if somebody wants to add it. So if I give my pen potential energy, let go of it to give it kinetic energy, and it hits the ground, I can't destroy energy. Where'd that energy go? Potential, kinetic, ground. Where's my energy go? To the ground as heat. Yes. So when I hit the ground, all that kinetic energy is transferred into the ground. It makes all the atoms in the ground vibrate, which heats up the atoms. So if you had like a super specific, super expensive thermometer, and it would have to be incredibly expensive to measure the difference, because the difference is so tiny. But if somebody dropped a pen on the ground and you had a thermometer pointed at that exact spot, what you would see is that that ground heated up. It's tiny amount, but that's what happens. And all the energy will dissipate into the surroundings, right? And basically all that heat will be transferred. Right? So if I would jump up and down right now, all the kinetic energy putting in the ground would eventually go to heat. The same when a tank round hits the Soviet. Yeah, sure. That is the same principle, yes. All right. Last type of energy, though, and I can't describe this by doing like motions, is chemical energy. So chemical energy is really potential energy, but it's potential energy due to atoms being bound. Whoops. So gasoline is the easiest example for this. Gasoline has a lot of bonds that have high energy. And when we break those bonds, we can utilize that energy. And we use that energy to move a car, for example. So chemical energy is potential energy due to how atoms are bonded to each other or the position of atoms. So those are our 4 types of energy: kinetic, movement; thermal, temperature; potential, position; chemical, a type of potential energy that is just for chemistry. All right. So the first thing we're going to do is we're going to do just some simple energy units, right? So when we talk about food, the energy you talk about is the calorie. Really, it's a kilocalorie. So they don't really say. If you go to Europe and you look at the bottom or the back of their food, they'll have all their units as either kcal, or actually they can have kilojoules as well. In America, we don't. We just call it the calorie, but that's kind of deceptive because a calorie is a kilocal. It really doesn't matter, but that's just for your knowledge. So in science, we don't use a calorie. We use what's called the joule. Joule is our unit of energy. So let's say after class, you decide to go to Mickey D's, right? And you got a Big Mac, you got a medium fry, and a medium Dr. Pepper, which is 1,080 calories. What I want you to do is tell me how many kilojoules this is. And if it takes 23 watts an hour to run a light bulb, based on that lunch, how many hours can you run a standard light bulb for, given these conversion factors? So we're just going to do a little unit conversion here to begin with. So let's see if we can do that. All right, so our first problem, hopefully we're really comfortable doing conversions, even though we've never done this conversion before. It's no different than what we've been doing. Right? So we have 1,080 calories. 1 calorie is 4.104 joules, which is given the unit of J. And there are 1,000 joules in 1 kilojoule. Yeah, so it'd be 4,432 joules or 4.432 kilojoules. Now, let's say if you could take all that food and extract all the energy from it to power a light bulb, how many hours can we get out of that light bulb? All right. So this is a longer unit conversion, which does take a little bit thinking about, but let's walk through these steps, right? So I start with my amount of calories. I got 1,080 calories. And I want to go to watts, right? Because a watt is the unit that my light runs in. It runs in 23 watts per hour. So my first thing I need to do is convert my calories to watts. So that is 0.860 cal for every 1 watt. Then how much energy does a bulb take? There are 23 watts for every 1 hour. So that's how much energy a light bulb takes. And if I look at my train tracks, right, calories have canceled out, watts have canceled out. I'm left in a unit of hours, which probably means that I did my conversion right. So if I multiply everything on the top divided by everything on the bottom, what you find out is that from a number 1 at McDonald's, you could run your light bulb for 54.6 hours or about 2 days and 8 hours. That's how much energy is contained in that. So any questions about our unit conversions here? Again, I would never expect you to memorize these conversion factors. I will give those to you. All I expect for you, though, is to be able to convert between everything if given those units. So questions about that? All right, relatively simple. Now, when we talk about energy in chemical systems, we are really talking about internal energy. And internal energy is just the sum of kinetic and potential energies of the system. So everything in the system, all the particles in the system will have their own kinetic and potential energy. And the internal and the entire internal energy of the system is just the sum of all of those. And when we talk about energy, energy is what's called a state function. And what a state function is that it only depends on the final and initial states. And the easiest way I can explain this is a person climbing a mountain. So when you're on a mountain, right? If we talk about potential energy, the higher you are on the mountain, the more potential energy you have. So let's say there's 2 people, person 1, and I guess I'll use a different color, blue, person 2. So person 1 decides to do a zigzag up the mountain. And let's say it takes them like 20 hours to do that. They do this in multiple steps. So that's a 20-hour path. Person 2 just climbs straight up the mountain. And that takes them like 3 hours to do. If we're talking about potential energy, the change in potential energy for both people are the same, since they're at the both same points of the mountain. They started at the same point and they ended at the same point. So a state function is that the change does not matter on the path. You can take any path that you want. All that matters is where you started and where you ended. Does not matter the in-betweens. If person 3 was on the bottom here and they took a helicopter up to the top, their change in potential energy is the same as person 1 and person 2. It's path independent. Only starting position and ending position matter. And when we talk about energy changes in chemistry and in science, we're talking about delta E, right? What was your energy at the final minus what was your energy at the initial? And it's always that. Every time you see a delta in this class, it's always going to be final minus initial. Delta, by the way, anytime you see delta as well, that means change, right? So this triangle is the Greek letter delta. Delta in science, whenever you see that, means change. And whenever we're doing that, it's your final state minus your initial state. For chemistry, when we want to do the change of energy of a reaction, it's always products minus reactants. So products are your final state, reactants are our initial state. And just as another reminder, if we do A plus B go to C, the left side are our reactants, and the right side are our products. All right. Any questions with the information that I presented there? All right. So here we already talked about some of these, so I'm going to go through briefly. When we talk about energy, change in energy of our system, it has to come from our surroundings because we cannot create energy. So any energy, you can see it right. Any energy change in our system has to be from our surroundings. Therefore, the change of energy of our systems is equal in magnitude to the change of energy of our surroundings, just a different sign. So for example, if our system gained 20 kilojoules, it had to lose 20 kilojoules. If our system lost 50 kilojoules of energy, the surroundings gain that energy, right? Because we cannot create energy, so it has to come from somewhere. So if we gain energy in our system, it came from our surroundings. If we lose energy in our system, it goes to our surroundings. That's all this slide is saying. Can we get the formula sheet for exam 3 already? I don't know about that because it's not made, right? So usually I make that like when I make the exam. I can look at doing that, but do keep in, well, I don't know. I'll have to get back at you with that because I do not make those. Like what I literally do is once I know all the PowerPoints that are on the exam, I just go back and copy paste, copy paste, copy paste, copy paste, copy paste. So that's why I don't like make them beforehand. But yeah, that's the delta energy of the system, delta energy surroundings. I mean, what you could be doing right now along with that is every time you see a equation, just copy paste it and kind of like write a note down to what equation it goes with. All right. So question 2 I do have a poll for this, but what I'll do again, I'll give you, I know the poll can cover up the question. So I'll give people like a minute or two to read this, write down your answer. Don't put it in chat, write it down, and then I'll make a poll. So if I have energy that's flowing out of a system and into its surroundings, what is the sign of delta E system? And is this endo or exo? B, if the internal energy of the products of a reaction is higher than the energy of the reactants, what is the sign of delta E? Is this endo or exo? So again, take a minute, try to answer this, and then I'll put up a poll so I can see where our understanding is on this topic. Okay. So I actually have the questions rewritten on the poll, but here we go. Here's the two questions, and each one only has 4 possible answers. Either the change in energy is positive or negative. Is that endo or exothermic? So I couldn't do the delta sign on the poll. I guess I could have, but I didn't. So the DE means delta energy. I'll do about another minute for this. All right, so let's take a look at this. So question 1, we have energy. Let me get my pen back out. We have energy flowing out of the system. So that means my change in energy was negative. I lost energy. And if it's flowing out, it is exiting, so it's exothermic. While 2, I have the energy of the products are higher than the reactants. So for here, delta E equals products minus reactants, and we can put fake numbers on there. So if the product is 100, and the reactants were 50, delta E is positive. And if I'm positive, that means I'm taking in energy if delta E was positive. So that's an endothermic process. So yes, positive and endothermic as well. Questions about that idea? All right. There's no questions. Well, it seems like there's a question. B is endo. Energy is going into the system. Delta E is positive and is endo. Yep. So if delta E is negative, that's always exo. If delta E is positive, that's always endo. All right. So if there's no more questions, this time I will remember to put up a homework, even though I didn't on Friday for some reason. So I will put up a homework this time. Other than that, as always, if you have questions about anything, please just shoot me an email. I'll be happy to answer those. But yeah, that's all we have for today. So have a good rest of your week. Catch people on Wednesday.